So now we know about the sine and the cosine function. We need to learn about the other 4 trigonometric functions, which isn't too bad since we already know the sine and cosine. So there are 4 more trigonometric functions. They are the tangent function, which we abbreviate TAN, the cotangent function, which we abbreviate COT, the secant function, which we abbreviate SEC, and the cosecant function, which we abbreviate CSC. So we define these in much the same way we do the sine and cosine, in that we look at where the terminal side of an angle hits the unit circle. So if an angle is in standard position and XY is a point of intersection of the terminal side of the angle and the unit circle, then the tangent, cotangent, secant, and cosecant function are defined as follows. The tangent of theta is equal to y over x, cotangent of theta equals x over y, secant of theta equals 1 over x, and cosecant of theta equals 1 over y. So we're basically using the same idea of looking at the point where the angle hits the unit circle, but rather than just look at the x or the y coordinate, we're really looking at either a combination of those 2 coordinates or 1 over the x or 1 over the y. The nice thing about this is there's not more points that you're going to have to learn. You know your unit circle points at this point, at least you should. And you're going to use those same points to develop the answers for these 4 trigonometric functions. Now there's one issue with this, is that these functions are all defined in terms of fractions. Well, if they're defined in terms of fractions, there's a problem when it comes to fractions, and that is that some fractions' denominators could end up being 0, and you don't want that. Well, look at this. Tangent has x in the denominator, secant has x in the denominator. If x is ever 0, if we're looking at a point, if we have a graph like this, and we have this unit circle, and we have our angle, theta, that angle hits a point, xy. If that x coordinate for this point is ever 0, then these 2 functions would have 0 in the denominator, and if they have 0 in the denominator, these would be undefined. It didn't happen with sine and cosine. Sine and cosine are never undefined because they're not defined by fractions. They're either just defined by solely the x or the y. But now these are y over x, 1 over x. If x is 0, tangent and secant are undefined. Same thing goes with y being 0. If y is 0, cotangent and cosecant are undefined. And that's something we're going to talk about in a little bit more detail in a couple seconds. All right. First, we can basically look at the tangent, the cotangent, the secant, and the cosecant in terms of sine and cosine. Remember, sine is equal to y and cosine of theta is equal to x. Well, if tangent of theta is equal to y over x, then I can really look at it as sine over cosine. Cotangent's x over y, so I can look at it as cosine over sine, so on and so on. Okay? So what happens is these new 4 trigonometric functions that we just talked about are really going to be defined in terms of the sine and cosine, and that's why knowing the sine and cosine already makes dealing with these a little bit easier. So here's our unit circle. You should have this unit circle down by now. You should know what the points are that go with which angles to be able to evaluate these trigonometric functions. So if I said, find the tangent of pi 6, okay? Well, here's pi 6. Here's the point that goes along with pi 6. Since I know that tangent is y over x, tangent of pi 6 is going to be the y coordinate, which is 1/2, divided by the x coordinate, which is square root of 3 over 2. Well, if I'm dividing a fraction, I'd flip and multiply. The 2's cancel. I get 1 over the square root of 3. Normally, we shouldn't have roots in the denominator, so you're probably not going to see the answer written that way in most cases. So then I'll rationalize this, multiply by square root of 3 over square root of 3. And I end up with square root of 3 over 3. So the tangent of pi 6 equals the square root of 3 over 3. How about let's do another one? How about we find the secant of 5 pi fourths. Okay. Well, if we look at this, secant is 1 over x. Here's 5 pi fourths. Here's the point that goes along with 5 pi fourths. So we're going to take this and say, well, this is 1 over negative square root of 2 over 2. Again, divide by a fraction, I get 1 times negative 2 over the square root of 2. So negative 2 over the square root of 2. I should then rationalize that. And I get negative 2 square root of 2 over 2. These 2's cancel, and I get negative square root of 2. So if you know your points, and you know how to define these four functions, you can do the same thing we've been doing all along now with these four functions. But here's what you got to watch out for. If I say find the cotangent of pi. Cotangent is defined by y over x. Here's pi. Here's x over y. Here's pi. Here's negative 1 over 0, negative 1, 0. And if I did that, negative 1 over 0, I get something that's undefined. Alright, that's fine. You can get an answer that's undefined. Well, what does that mean? It means that I can't take the cotangent of pi. Pi cannot be in the domain for this function because I don't get an answer out of it. So we'll have to discuss that about domains for these four trig functions. So you're going to see questions like this that say find the value for all the 6 trigonometric functions for each angle. So what this is asking you to do is to find the sine of pi thirds, the cosine of pi thirds, the tangent of pi thirds, the cosecant of pi thirds, the secant of pi thirds, and the cotangent of pi thirds. Alright. Now I write it down this way for a reason. These functions are all related. Okay? And the way I write my answer down can help me find my answer. So when I look at this, I go, okay, let's find sine and cosine first. So I think about my unit circle. Here's pi thirds. Here's my circle. And I gotta know what's that point. Okay? Well, that point is a half square root of 3 over 2. Okay? That's my point. So that means sine is square root of 3 over 2. And cosine is a half. And really what you're looking at is, this is the y coordinate. And this is the x coordinate. Right? Well, think about how these things are defined now. Tangent of theta is y over x. Well, if it's y over x and I know my y and my x, if I just take this value divided by this value, I'll get this value. And that's why I stack these up vertically like this, because once I find sine and cosine, I can get tangent out of that by doing sine divided by cosine gives me tangent. So if I look at that, I go, alright, well, if I take square root of 3 over 2 and divide it by a half, I have square root of 3 over 2 times 2 over 1. I cancel, and I get square root of 3. Alright, now I can do the same thing for these. There's a reason why I list cosecant across from sine, secant across from cosine, and cotangent across from tangent. Because if sine of theta equals y, cosecant of theta equals 1 over y. So the cosecant is the reciprocal of the sine. So if I know this answer here, to get this answer, I should just do the reciprocal. I should do 1 over y. So in that case, what I'm going to do is say this answer is 2 over the square root of 3. And by writing it this way, I can clearly see that pattern. These are the reciprocals, and these you divide. Now, I'm not going to write my answer as 2 over square root of 3. I'm going to rationalize it. So I get 2 root 3 over 3, but still, there's my answer. Secant of pi thirds, that's the reciprocal of cosine. Cosine is a half, flip a half over, I get 2. Cotangent, cotangent is reciprocal of tangent, because if this is y over x, this one is x over y. So basically I just take this thing and flip it over, so I get 1 over the square root of 3. Rationalize it, and I get the square root of 3 over 3. Let's erase some of this so you see it better. So here are my answers. Sine of pi thirds is square root of 3 over 2. Cosine of pi thirds is a half. Tangent of pi thirds is square root of 3. The cosecant of pi thirds is 2 square root of 3 over 3. Secant of pi thirds is 2. Cotangent of pi thirds is square root of 3 over 3. Okay? So oftentimes the way you write it down can make it easier for you to come up with all 6 of the answers. And once you know sine and cosine, you really got the other 4. So let's do another one. How about 135 degrees? So if I want to find the sine of 135 degrees, the cosine of 135 degrees, the tangent of 135 degrees, the cosecant of 135 degrees, the secant of 135, and the cotangent. Alright, so first I gotta do sine and cosine. Well, where's 135 degrees? So here's 135 degrees. What point am I looking at there on the unit circle? Well, that's going to be negative square root of 2 over 2 for the x and positive square root of 2 over 2 for the y. So sine's going to be square root of 2 over 2. Cosine's going to be negative square root of 2 over 2. And tangent is the y divided by the x. So if they're the same, just one's negative, I'll get negative 1. Alright. Cosecant. Cosecant's reciprocal of sine. So I'm going to just flip this over. 2 over the square root of 2. Rationalize it. And I end up with square root of 2. Same thing for the cosine, but it's the same, just negative. So negative square root of 2. And if I flip negative 1 over, I get negative 1. So here are my answers. Square root of 2 over 2, negative square root of 2 over 2. Negative 1, square root of 2, negative square root of 2, negative 1. It's very fast to find these values if you set it up a certain way and you know your points. Now that we know how to define the other 4 trigonometric functions, we need to graph these trigonometric functions. And again, since we know how to graph sine and cosine, it's going to make it much easier to graph these other 4. In order to do this, we need to talk about something though, something called a vertical asymptote. So when we look at a vertical asymptote, in just algebraic terms as it relates to any type of function, a vertical asymptote is a vertical line that your graph will approach and then turn to positive and negative infinity. It goes like this. So I have some graph, okay? Here's my x-axis, here's my y-axis. So then here's some x value, and there's a vertical line through that x value. As my graph gets closer and closer to this x value, whatever it's doing, it doesn't matter, it can do anything. As it gets closer and closer to this x value, if my graph turns up to positive infinity, or vice versa, down to negative infinity, okay, that vertical line is what we consider to be a vertical asymptote. And the same thing on the other side. My graph is either going to go up or go down. My graph cannot cross over that line. That line is like a wall, and my graph, when it comes close to that wall, wants to veer off. Now, if it veers up on one side, it can go down on the other side. Both sides can go up. It doesn't really matter. But the idea is if there's some vertical line, x equals a, it would be considered a vertical asymptote for the graph of f of x if f of x goes to positive or negative infinity as x gets closer and closer to a. When you see this arrow, it means that that's what these values are doing. They're getting closer to infinity, negative infinity, and a. So, again, just to reiterate, as my graph gets closer and closer to this vertical line, if f of x goes up to positive infinity or down to negative infinity, as I get closer and closer to this vertical line A, then this line is called a vertical asymptote. Now, when will these vertical asymptotes occur? Well, they'll occur when I'm looking at fractions and the denominator is 0, but the numerator is not. Okay? That's when you're going to get this. Well, since our functions are defined in terms of fractions, we're going to have vertical asymptotes for our other 4 trigonometric functions. So if we look at when our 4 trigonometric functions are undefined, that's where our vertical asymptotes are going to be located. So the key values to look at here are these 4 points on the unit circle. So this point is 1, 0, this point is 0, 1, this point is negative 1, 0, and this point is 0, negative 1. The angles that go along with that are 0, pi halves, pi, 3 pi halves, back to 2 pi again, right? So let's look at tangent. Tangent of theta is y over x. Secant of theta is 1 over x. Both of these have x in the denominator. If you look at these 2 points here, these 2 points have the x coordinate to be 0. So, if theta equals pi halves, or 3 pi halves, or anything coterminal to those, which would also be 5 pi halves, 7 pi halves, etc. These functions, tan and secant, are undefined. And therefore, whenever you see these triangle dots, it means the word therefore. And therefore, have vertical asymptotes at those values. Okay? So tangent and secant are undefined in the same places. They're undefined, and basically the easiest way to remember this is odd multiples of pi halves. Any odd multiple, 1 pi half, 3 pi halves, 5 pi halves, 7 pi halves, 9 pi halves, any odd multiple of pi halves will put you here or here, and those will have x values that are 0, and that would make these functions undefined. So if I said, what's the tangent of 101 pi halves? Since it's an odd multiple of pi halves, it's undefined. Okay? Alright, how about the other 2 trigonometric functions? Okay, so we have the cotangent, which is x over y, and the cosecant, which is 1 over y. Both of them have y in the denominator. Alright, well look at these 2 points now. Y is 0 in both cases. So that would put 0 in my denominator, make them undefined, and therefore give me a vertical asymptote. So if theta is 0, or pi, or 2 pi, or 3 pi, or 4 pi, etc., these functions are undefined. And therefore have vertical asymptotes. Okay. And the easiest way to remember this is these are all whole number pi's. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. They're all whole number pi's. Cotangent and cosecant are undefined at those whole number pi's and have vertical asymptotes at those whole number pi's. So now we're ready to start looking at the different functions in the graphs. Alright, so we know vertical asymptotes, where the function's undefined. Tangent, sine over cosine, or y over x. Tangent is undefined at those pi halves, all those odd multiples of pi halves. This is one way we could write it, okay? But it's much easier for you just to remember odd pi halves. So if I look at that and I say, okay, well here's, say, pi halves. Here's 3 pi halves. Here's 5 pi halves. Back here would be, say, minus pi halves. Okay. Each one of these values, I'm going to have a vertical asymptote. It's where tangent's undefined. I have one of these vertical lines. They should all be equidistant away from one another. My graph doesn't look that great, but it should be equidistant away from one another. What happens is my graph in between those values ends up looking like this. And then it'll repeat itself again and again and again, over and over and over again, infinitely many times. Okay? Remember, your graph has a period, and the period is the amount of time it takes for the graph to repeat itself. So, if you look at this distance right here, that's how long it takes for the graph to repeat itself, because then it's going to start over again and again and again. Well, that distance from here to here is pi. So the period for this function is pi, which is different from sine and cosine. The period for the sine and cosine graphs was 2 pi. These functions will repeat every pi units. Okay? But generally, this is what my graph looks like. Now, if we only want to look at one period, most of the time we'll just look at this particular period right here. But this is my graph. Key points. Your graph has 3 key points. Remember, the sine and cosine had 5 key points. These graphs only have 3 key points. They have your intercepts, which are in between each one of those vertical asymptotes. So there's one x-intercept, and then there's your vertical asymptotes. If I know those 3 things, if I know where this asymptote is here, and I know where this asymptote is here, and I know this point, I can draw the graph that I want to draw. So my key points are going to be negative pi halves, 0, and pi halves. The ones on the ends are my vertical asymptote, and the one directly in the middle is my x-intercept. So if I want to start graphing this tangent function, I should look at a tangent function that has multiple things happening to it. Something like this. D plus a tan b x minus c. Well, we know what a, b, c, and d do to the sine and cosine. Well, they're going to do the same exact thing to the tangent function. A is going to affect the amplitude. B is going to affect the period. C is going to be the phase shift. D is going to be the vertical shift. Now, there's a small difference between the sine, cosine, and the tangents. 1. Amplitude. Amplitude doesn't have an effect on the tan function that it has on the cosine and sine function. Because the tan function is already a vertical function that looks like this, if I stretch this thing vertically, it's still going to go from negative infinity to positive infinity. Whereas the sine and cosine functions, if I change them vertically, it changes their range. 2. Period. Normally to find the period, we would do 2 pi divided by b. That would be for sine and cosine. But that's because the old period was 2 pi. The period for tangent is only pi. So to find the period for tangent, we're just going to take pi and divide it by b. Okay? And if we want to do this whole thing at once, where we do the change in the period and the phase shift, normally for sine and cosine, we take that bx minus c, set it equal to 0, and bx minus c and set it equal to 2 pi. But that's... excuse me. Alright, so that was because the original function would start at 0 and end at 2 pi for sine and cosine. That's not the case for tangent. So we don't use 0 and 2 pi, we use the vertical asymptotes, which is where the tangent starts and ends, which would be negative pi over 2 and positive pi over 2. And if we ever want to find the x-intercept, it's always the midpoint between the asymptotes. So this will help us find the asymptotes, and then the midpoints directly in between. Alright. So let's put a graph together. So if I want to graph tangent of 4x minus pi halves. Alright, what do I need to know? Well, I gotta look at this thing and say, alright, let's look at this piece right here. This right here is going to affect my period and my phase shift. Now, the period is not 4 and the phase shift is not pi halves. If I want to find the period, I use this value, which is b, and I'm going to take pi and divide it by b. So in this case, I'm going to take pi divided by 4. That's my period. Also, pi over 2 is not the phase shift. I have to look at this as b times x minus c. So if I want to find the phase shift, I would do 4 times x minus pi over 8. If I multiplied the 4 in, I would get pi over 2. So my phase shift is pi over 8. Now that's all well and good, but I still have to use that to draw my graph. So if you're really just trying to draw your graph, you don't really have to do a whole lot of this. What you're going to have to do is take this 4x minus pi over 2, and you're going to have to set it equal to minus pi over 2. And 4x minus pi over 2, and set it equal to positive pi over 2. This is so that we can find my endpoints. And the endpoints are my vertical asymptotes. So I solve these equations. I'll take 4x, I'll add pi over 2, I get 0. So x equals 0. That's one endpoint, which is one vertical asymptote. I'll add pi over 2, I get 4x equals pi. Divide by 4, I get x equals pi fourths. That's my other asymptote, my other endpoint. Remember, the distance between these endpoints should be the period. That's clearly the case. So now I want to put my graph together. So I look at this and I go, okay, I want to graph tan, or y equals tan, of 4x minus pi over 2. So we said one endpoint is at 0, the other endpoint is at pi over 4. These are vertical asymptotes when it comes to the tangent function. Directly in the middle, which is pi over 8, is my x-intercept, and my graph should go accordingly. That's pretty bad. Hold on, let me erase that again. Let's try that again. My graph should go accordingly, and that should be the graph of my tangent. Now that's just one period. My graph's going to do this again, and another vertical asymptote, and again, and another vertical asymptote, over and over and over again. But this right here would be the graph of one period of the tangent function. And as you can see, graphing the tangent is actually much easier than sine and cosine because there's less to the graph. There's only three key parts to it: the two vertical asymptotes on the end, and the point directly in the middle, which is your x-intercept. Next up is the cotangent function. So for this cotangent function, if you know how to draw tan, it's actually very similar. Cotangent is the reciprocal of the tangent. So what happens is a lot of things look the same, but it is undefined in different places. This function will be undefined at all those whole number pi's. So we write it like this: theta can't be k pi. That's where my vertical asymptotes are going to be. That's where it's undefined. So 0, pi, 2 pi, 3 pi, back here minus pi. Okay, these are all the places where my cotangent function is undefined, which means these are where my vertical asymptotes are going to be. And it's the reciprocal function, which means, in a way, it's flipped over from the tangent function. Now, that's not completely right. The general idea is when it gets closer to 0, the other function gets closer to infinity. But if I just show you the picture, it sort of makes more sense than in that. Oh, that's pretty terrible. Let's try that again. This is what the cotangent function looks like. It has a very similar shape to the tangent graph. It's just going in the opposite direction. It's a decreasing graph instead of an increasing graph. Directly in the middle of each one of these vertical asymptotes is where I should have my x-intercept. Some of these aren't so great. So let's try this one again. But that's what my cotangent graph looks like. This would be one period of the cotangent graph. The period is pi, so it's very similar to the tangent graph. If I want to find my key points, I'm going to have to use this idea of setting bx minus c equal to the original vertical asymptotes, which are 0 and pi. And the concept is these are the things that are moving. If I shift my whole graph down this way or this way, these vertical asymptotes are moving, so the ends of the graph are moving. If I stretch my graph out this way or this way, these endpoints are moving. So if this thing's going to do that, I set the bx minus c equal to the old endpoints, 0 and pi, and that'll tell me where the new endpoints go. And this is something you're going to have to keep straight. Bx minus c equals 0 and 2 pi for sine and cosine. Bx minus c equals negative pi over 2 and positive pi over 2 for tangent, and 0 and pi for cotangent. So what these numbers are changes depending on the function, and the reason why it changes is because you got to look at the original endpoints for whichever function you're dealing with, and then those are the things that you're going to change, and the endpoints for all our function are a little different. But once I have that down, graphing it isn't too bad. So if I said sketch the graph of this function, alright, normally we call that value A, this 1/3 would be my B, and -2 is not C, but that's going to help me find the phase shift. Alright, so what am I going to do? I'm going to say, let's find the period. I should do pi divided by B because it's a cotangent function. B is 1/3, so pi divided by 1/3 is going to be 3 pi. Alright, so now I know my period. The whole purpose of finding that is so that when I find my endpoints, I can use this to check that. So I do x over 3 minus 2. I'm going to set that equal to 0, and x over 3 minus 2 equal to pi. 0 and pi, because this is cotangent, and those are the endpoints of cotangent. I solve this. X over 3, if I add 2, equals 2. Multiply by 3, x equals 6. Do it again. X over 3, if I add 2, is pi plus 2. Multiply by 3, I get x equals 3 times pi plus 2. Now you look at this and go, alright, well, how can I use these endpoints and make sure that the distance between them is this? Well, if I multiply this out, what do I get? 3 pi plus 6, right? Is this one 3 pi more than this one? Yes. So the distance between them is 3 pi, so then it all does check out. This is one vertical asymptote, this is another vertical asymptote. So I go to sketch my graph. So we have y equals 2 cotangent of x over 3 minus 2. Cotangent. We said that 6 is going to be one vertical asymptote. The next one's going to be 3 pi plus 6. And that's just some number, so it's somewhere down here. This is a vertical asymptote. This is a vertical asymptote. Directly in the middle is an x-intercept. I'll draw my graph like this. And there you go. Now this 2 here out in front really does not affect the graph at all. It stretches the graph this way. But since the graph is already a vertical graph, it's not going to change the way you graph it. It doesn't change the y values that you label, because you don't label y values here. So essentially for tangent, cotangent, that value can really be ignored when you're trying to draw the graph. The only thing I would want to look at would be, where is this x-intercept? Well, this x-intercept's directly in between these two. So if I add these two together, 3 pi plus 6 plus 6, divide by 2, that'll tell me where that is. Well, this is 3 pi plus 12 divided by 2, and you know what? That's how I'm going to leave it. That's the x value right here. Right? If you wanted, I could write that as 3 pi plus 3 pi over 2 plus 6. But generally that's, could be left this way. So there's your graph of your cotangent function. So the last two functions up are the cosecant and the secant function. So we want to graph each one of those. Well, what we could do is learn 2 more graphs and 2 more periods and 2 more sets of endpoints, but we're not going to. Since cosecant is equal to 1 over sine and secant is equal to 1 over cosine, since we know how to work with sine and cosine in their graphs, we're just going to use that to help us draw cosecant and secant. Alright, so first of all, vertical asymptotes. If cosecant is equal to 1 over the sine, that means whenever the sine is equal to 0, cosecant is going to have a vertical asymptote. And the same thing here for cosine. Secant is equal to 1 over cosine, so when the cosine equals 0, the secant is going to have a vertical asymptote. So in order to draw these, what I'm going to do is first look at, let's do cosecant. So if I want to draw y equals the cosecant of x, first I'm going to draw y equals the sine of x. In that case, I would get this. That's what my sine function looks like. Here's 0, here's pi, here's 2 pi, here's 3 pi. This would be minus pi back here. Here would be pi halves. This would be 3 pi halves. Right, remember it maxes out at 1, mins out at -1. Alright, now where the sine is equal to 0, now is going to be where the cosecant is undefined, or cosecant has a vertical asymptote. Well, if a function's ever equal to 0, it has an x-intercept. So sine has an x-intercept here, 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 etc. Those x-intercepts are going to be vertical asymptotes for the cosecant function, which matches up with what we already said in that the cosecant will be undefined at the whole number pi's. Alright, next what we want to do is then completely draw the cosecant graph. We have the vertical asymptotes for the cosecant graph. Now we're going to draw the cosecant graph. And let me put the graph together and then I'll explain why. So the cosecant graph I'm going to draw in red. Okay? So what I'm going to do is base my cosecant graph off my sine. And essentially what happens is this point right here is on my sine. That's pi halves comma 0. Well, that's actually going to be the exact same point on my cosecant graph as well. But my cosecant graph is going to look like this. Same deal here. That's on my sine graph. That point is also on my cosecant graph. And my graph's going to look like this. So what I'm doing here is I'm using my sine graph to fill in what my cosecant graph looks like. And my cosecant graph is a series of what look like parabolas. And they're placed on the ends of the sine graph. So if you look at this, if I could draw my sine graph, I could draw my cosecant graph by knowing the relationship. Now why is this happening? The reason why this happens is this. The cosecant is the reciprocal of sine. It's 1 over the sine. If I look at what's happening with the sine function here, the sine function is getting closer and closer to 0 as far as its y value goes, as I follow it downward. Okay? Well, as this function goes close to 0, the reciprocal does the opposite, goes further away from 0, goes closer to positive infinity. And the same thing here. The y values here are getting closer to 0. Well, the reciprocal of those numbers goes the opposite way, gets bigger. So that's why I'm basically sort of flipping over this sine graph as a parabola. Now, this point right here is pretty important also. The y value there is 1. If I take the sine of pi halves, I get 1. Well, if I want to take the cosecant of pi halves, I should do the reciprocal, but the reciprocal of 1 is 1, and that's why that point stays the same. So this is the basis for the cosecant graph. Now you know what the cosecant graph is, we can then alter that cosecant graph, really by altering the sine graph, drawing that, then filling the cosecant graph in there. Every time I have an x-intercept, put a vertical asymptote. And then once I have those vertical asymptotes, put my inverted parabolas on the ends of my sine function. We do the same thing for cosecant, or for secant. Secant x equals 1 over cosine x. Cosine looks like this. Okay. It's here 0, here's pi halves, here's pi, here's 3 pi halves, here's 2 pi, etc. My x-intercepts are here, 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 and so on. Where those x-intercepts are going to be my vertical asymptotes for my secant graph. And then my secant graph is going to be inverted on that cosine graph. And it just looks like a series of parabolas approaching these vertical asymptotes. The blue graph is my cosine, and the red graph is my secant. If I have my cosine graph I can draw my secant graph off of that. I think maybe a couple of examples might clear some of your questions up a little bit more now. So let's draw the graph of this function. This is a cosecant function, and it's 2 cosecant x plus pi fourths. Now in order to do this, what I'm actually going to do first is draw y equals 2 sine of x plus pi fourths. And then I'm going to fill my cosecant graph into that. So now what do we know about this graph? This graph has an amplitude of 2. It has a period of 2 pi divided by b. b is this number, so 1, so 2 pi. And it has a phase shift of pi fourths. Okay? And sometimes you might see this as minus pi fourths, because usually you'll see this as x minus c. So that would be x minus pi fourths. But really you just know pi fourths, and since it's a plus, it's going to the left. Okay? Alright. Anyway, so what we do here is say, alright, well that's fine to know, but really we want to graph it, so we want to find the endpoints. So if I want to find the endpoints, I take this x plus pi fourths. Since it's a sine function, I set it equal to 0. And I set it equal to 2 pi. I get x equals negative pi fourths. X equals 2 pi minus pi fourths. Well, 2 pi is 8 pi fourths. Minus pi fourths gives me 7 pi fourths. So my endpoints are these endpoints. Remember, you got to make sure that that's the same as your period, and it is. The distance from here to here is 2 pi. So now I'm going to start to put my graph together. So I remember I want to draw y equals 2 cosecant of x plus pi fourths. But in order to do that, what I'm really first drawing is y equals 2 sine of x plus pi fourths. Alright, so I'm going to do this first one in blue, and I'm going to do the actual graph I want to do in red. Alright. So what do we know? The amplitude is 2, so I'm going to go from 2 to negative 2. I'm going to start at minus pi fourths. I'm going to end at 7 pi fourths. Directly in between that, which looks like right about there, is another x-intercept. Directly in between that there and that there is a maximum and a minimum. So I have this point, this point, this point, and I connect my dots. Not the best, but that's what my sign will look like. Now what are these values? You want to start to label them. Well, once I have the ends, I can find the one in the middle, this one right here, by doing 7 pi fourths plus negative pi fourths divided by 2. Anytime you want to find something in the middle, add together, divide by 2. So this is going to be 6 pi fourths over 2, 6 pi eighths, which is the same thing as, what, 3 pi fourths. So that's 3 pi fourths. This one's going to be pi fourths. This one's going to be 5 pi fourths. Alright, now once I have that labeled, I really want to draw my cosecant graph. Well, once I have these things done, the x-intercepts are my vertical asymptotes. Then I'm going to invert my parabolas on top of my sine graph, and that's going to be my cosecant graph. So again, the red picture is my cosecant and the blue picture is my sine. Really what you would probably want to do is then delete the sine graph, but it's not necessary because, you know, what we're looking at is 2 graphs in one. We know we need one graph to get to the other graph, but, you know, technically just the red graph is the cosecant graph and just the blue graph is the sine graph, but I put them together so that we can build one graph off the other. Remember that sine just repeats itself over and over again, so my cosecant graph is going to repeat itself over and over again, here, here, and so on. The period for cosecant is the same as the sine because my graph doesn't repeat itself until I get back to here again, so that distance is the same. Other than that, there's not much to the cosecant graph as long as you know how to draw the sine graph. Alright, so then let's do the secant, and then we should wrap this up. So if I want to draw y equals 2 secant 2x, okay? First, what I'm going to do is draw y equals 2 cosine x. Oops, sorry, no, 2. Just cosine 2x. Alright, well, what do we know about this function? That its amplitude is 1. It's going to have a period of 2 pi divided by 2, because this is my b. So that means pi. There is no phase shift to this. So if I want to find the endpoints to cosine, I'm going to say, alright, well, 2x equals 0 and 2x equals 2 pi. These will be my endpoints. So I get x equals 0 and x equals pi. If these are my endpoints, that distance should be the same as my period. That works out. Alright, I want to draw my graph. So remember, I want to draw y equals cosine 2x, but I'm doing that so I can draw y equals secant 2x. I'll do the same thing I did before. This one will be blue, this one will be red. Alright, so let's go here. Cosine. We said we're going to start at 0, and we're going to go to, I forgot it, let's go back, pi. Okay, 0 to pi. So we go 0, say here's pi. That's my cosine's endpoints. Cosine 1 to negative 1 starts off high, ends up high. Directly in the middle, it's low. In between those two are two x-intercepts. So my graph should look like this. That's cosine. Then what's going to happen here is I'm going to label some of this. Well, if this is 0 pi, this is pi halves, this is pi fourths, this is 3 pi fourths. Remember though, my cosine graph does repeat itself over and over again, but I'm just looking at one period. So now let's draw the secant. So x-intercept right here, do a vertical asymptote. X-intercept right here, do a vertical asymptote. There would be another one here, another one here, another one here, etc. Invert my parabolas on the ends of the cosine. This is what my secant graph looks like. So if I was going to draw one period of the secant graph, well, one period of the cosine graph would go from here to here, right? So this would be one period of the secant graph. I drew more than one period, but normally all you need is one period. So, much like the cosecant, the secant is drawn by drawing the cosine first, which is the blue graph, and then drawing the secant graph, which is the red graph. Normally, you would want to probably delete this cosine graph here, so that all you're looking at is the secant graph, but it's not really necessary, as long as you can tell the difference between them. So that wraps up our other 4 trigonometric functions. You should know how to evaluate those 4 trigonometric functions, and then also how to graph them.